Hello again, everybody. Welcome to another screencast lecture. Tonight's topic is graphing speed. Let's get started. First, we'll do a quick review of some important concepts that will help us with this lesson. First, we need to have a definition of motion. Motion is a change of position relative to a point of reference. And a definition of speed. Speed is the change in position and how long it took the object to make that change. Speed is often measured in units like miles per hour or kilometers per hour, centimeters or meters per second, things like that. Any distance per unit of time would be able to be a good unit for speed. And finally, velocity. Velocity is, it includes speed, but it also includes its direction. So you would say something like 12 miles per hour south. Now on for some new stuff. First of all, how is speed shown on a graph? You would use what's known as a distance time graph to represent speed. Time is going to be plotted on the x-axis. So as you go from left to right on the x-axis, time is going to increase, more time goes by. And distance is going to be plotted on the y-axis, so this would be like distance 0 and time 0. So 0 distance has been traveled when no time has gone by, and as time increases, often the distance that the object has traveled will increase as well. Time is plotted on the x-axis, distance is plotted on the y-axis. Go ahead and write this down on your notebook. Why is time plotted on the x-axis? Time is what's known as the independent variable in this case. And a good way to identify the independent variable would be to ask yourself, can time change if the distance does not change? Well, kind of more in plain English, it would be, can time go by even though the object is staying still? It's not changing its distance. And the answer to that, of course, is yes. I mean, I'm sitting here right here. Let's assume I'm not traveling anywhere, my position's not changing, so my distance is not increasing or decreasing from a certain reference point, but time is still going by. Then we'll take a look at distance. Distance will be the dependent variable. Can distance change if time does not change? The answer to that is no. You cannot change distance. You cannot change position without any time going by. So that would be like me saying, well, I'm here in my chair in front of the camera, and without any time going by, I'm going to change my position, and now I'm going to be at my desk at school. I can't do that. It requires time for me to travel to change my distance. I cannot be in two places at once. Doesn't matter, doesn't matter how much you want to be able to do so. Can't do it. Okay, here's a scenario. We have two students. Here's student A and here's student B. They're going to have a running race, and get ready for some amazing animation here. The race starts. Go. And here's runner letter A, and here's runner letter B. After 1/2 of a second, after 0.5 seconds, runner A has traveled 0.5 meters, and runner B has traveled half of that, so 0.25 meters in 0.5 seconds. Time 1, they continue at the same rate of speed, so you have the runner student A has traveled a total of 1 meter in 1 second, and runner B has traveled in the first second they traveled, or first half second he traveled 0.25 meters. In the second half of a second he goes the next 0.25 meters, which is a total of 0.5 meters. And this continues at the same rate of speed. So after 2 seconds, let's go back to that. So after 2 seconds, runner A is at the finish line, and runner B is halfway to the finish line. Here's a graph that depicts what we just saw. At 0.5 seconds, the runner A, letter A, the girl, had traveled 0.5 meters. At 1 second, the runner, the girl, had run 1 full meter, whereas student B, the boy, at 0.5 seconds only traveled half of a meter. Is student A moving or standing still over the 2.5 seconds of time? How can you tell if the student is moving or standing still? Well, we can see here by looking at the graph that student A is moving. She is changing her position. For example, at time 1 second, here's time 1 second, she was at meter marker 1 meter, and at time 2 seconds, she was at 2 meters. So every second that goes by, she is able to travel a distance of 1 more meter each time. How long did it take student A to travel 1 meter? Okay, student A traveled 1 meter in how much time? Well, you find 1 meter, you go across, and you hit the line that says student A, and then you come back down to where that meets at the x-axis. So it took 1 second for student A to go 1 meter. If we wanted to figure out the same thing for student B, you'd go 1 meter, go across here, it hits the line, go down here. You see that it took 2 seconds for student B to travel 1 meter. How far does student A travel in 1.5 seconds? Now this time we're going to look at the x-axis. We're going to start at the x-axis and we're going to go to 1.5 meters. And then we're going to go up until it hits the line here where it says student A. And then we see that it's at 1.5 meters is where student A would have traveled in 1.5 seconds. Student B for 1.5 seconds is right here. So you take this across and you'll see that student B would have traveled halfway in between 0.5 meters and 1 meter. So that would be 0.75 meters. So student B traveled 0.75 meters in 1.5 seconds. Our next question is what was student A's average speed? Well, to be able to calculate average speed, we need to know the formula for speed. Speed is equal to distance divided by time. So we're going to figure out the total distance traveled. So to be able to calculate the average speed for student A, you're going to take the total distance traveled, which is 2.5 meters. We're going to divide that by the amount of time it took student A to travel 2.5 meters, and the answer to that is 2.5 seconds. You see you have 2.5 meters, and you divide that by 2.5 seconds, you get 1 meter per second. And you can see how I did it for student B as well. So speed is equal to distance divided by time. The speed is equal to 1.25 meters. That's how far that student B went, and we divide that by how long it took student B to do that. It took student B 2.5 seconds to make that trip, and it comes out to be 0.5 meters per second. So it's half of a meter per second is its speed. So in 1 second, it would travel, or he would travel 0.5 meters. After 2 seconds, he would have traveled 1 meter. All right, student A's speed. What happened to student A's speed over the journey? Well, what you want to do is if you see a straight line like this, it's a constant slope where every second that goes by, so here's 1 second that goes by, the runner travels the same distance from here to here, and then from here to here. It's called a constant slope, and if the speed graph has a constant slope, that means that the object or the car or the dog or whatever it is that we're measuring the speed of, this means that it's going to have a constant speed. Now let's take a look at this graph. It's the same graph, but in this case I actually whited out the numbers that go on the x and the y axis. We can still tell which student A or student B is running faster just by looking at the graph. So what you do is you look for how steep the line is, how steep the slope is. That means that the distance is changing more per unit of time. So if you take a look at this line for student A, it's this unit of time. For student B, it's this unit of time. They're both going over the same unit of time we're going to compare. But this line, student A's line, is steeper than student B's line because student A, the distance is changing more in the exact same amount of period of time than student B. So in this case, student A is traveling faster than student B. And imagine a car that is not moving. What would the speed graph look like? If the car is not moving, that means that as time goes by, how is the distance changing? Well, it's not moving. It's not changing position. There is no motion. There is no difference in position. So the distance is just going to stay the same. So wherever the car is, it's just going to be staying the same over that long period of time. And that's going to be a horizontal line is going to be shown on a speed graph. So if an object is not moving, a horizontal line is shown. Imagine a car that is moving at a constant speed. What would the graph look like? Constant speed is going to be shown by a straight line. So if it's a straight line, it is going to tell you immediately that the speed is constant. And we already mentioned to you that if the line is steeper, that means that it's a higher constant rate of speed. Imagine a car is moving at a constant speed backwards towards the starting point. What would the graph look like? When you make a distance time graph, you're really using some sort of a point of reference, and normally we're going to use the point of reference as the starting line of a race, or maybe if you're trying to figure out the speed going on a trip. So maybe you would start at home. Home would be your starting point. Home would be your point of reference. So as time goes by, your distance is getting further and further away from your home. Now, let's say you get to school and you spend the day there, and then you come home. You're actually going back towards your starting point, so you're losing distance. Now, you're not really having negative distance. You can't travel negative distance. However, that distance is getting closer and closer back to the starting point. This graph shows the constant speed of a car returning back to where it started from. So here's your starting line. Here's where the car is currently, and as time goes by, the distance is getting shorter and shorter away from the starting point. Imagine two cars traveling at a different but constant speeds. What would the graph look like? First of all, they're both constant speeds, so we know that both the lines need to be straight lines, but they're traveling at different speeds, so we know that speed can be shown or at least given a guess on how steep the line is. So they must have two different straight lines with two different speeds, and lo and behold, here we go. So this could be one car, here could be another car. Here you can compare the two. This is a steeper line than this. The purple line is the faster moving car. The distance is changing at a greater rate than the distance is changing for the red lined car. Here we have three different cars. We have the green car here, we have the purple car here, we have the red car here. Which car is traveling the fastest? Remember again, the speed of the car is determined by the slope of the line. This line has a greater slope. It's more towards the vertical than both the green and the red. In fact, the green and the red both have the same slope. So what we're going to say is that the purple car is going to have the fastest. It's changing in the greatest amount of time. The green and the red are traveling both at the same rate of speed because they both have the same slope. Let's compare the green car and the red car from the last graph. We see they're both traveling the same speed because they're the same sloped line. However, which car is leading the race? The green car is, because it started at time 0. It started at a position more forward than the red car. So let's say the green car started at the 20-yard line and the red car started at the 0-yard line. Imagine a car that is increasing its speed as time goes by. What would the graph look like? Since the car's speed is increasing, so the speed is not remaining the same. If the speed is not remaining the same, we know that it is not going to be a straight line. So that's kind of a hint for us. It's going to look like this. It starts off relatively slow, relatively flat, and then it starts going faster and faster and faster and faster and faster, and it's getting closer and closer to the vertical. This is a graph that shows the increase of speed of a car over time. Conversely, if the car is getting slower as it travels, we would expect the curve to do what? It's going to be going fastest here, so it's going to be more vertical here, and it's going to be slowing down, slowing down, slowing down until it gets closer and closer and closer to the horizontal line. This will be a good challenge for you to see how well you understand what we've gone through so far. We have 5 different letters, A, B, C, D, and E. What I want you to do is, on your paper, or at least in your mind, describe what is happening at each point. So, for example, the green car is letter A. At this point, how would you describe the car's motion? Both the direction it's moving away or towards the starting point, and is it moving at a constant rate of speed? Is it increasing speed? Is it decreasing speed? What's going on? Position and speed. I'll give you a little bit of time to answer that. You might want to pause this, Here's your answers. The green line shows a fast, steady speed. It's the fastest because it's the most steep. It's a steady speed. It's a constant speed because it is a straight line. Here, this is a constant steady speed here, and the car is going away from the starting point. Here, the car stops because the time goes by, but the distance does not change. And then finally, the blue line, you see that it starts off relatively slow, it's relatively horizontal, flat, and then it gets more and more vertical, it's getting faster and faster. Something like this might be like a rocket launch. So at the beginning of the rocket launch, the rocket is moving slowly. As it gets further and further away from the Earth, it's going to be moving faster and faster. Tricky one for you. What is the object? Let's say this is a car. What would this car be doing with this vertical, totally vertical red line? What do you think's happening? I'll pause it for a second and then think about it. And I will count down. 3, 2, 1. Well, first of all, this would mean that the car is at an infinite number of distances at the same time. So here's the time. The time does not change. So that would mean that the car is here at this distance, which could be like time at distance 0. Distance here, maybe let's say 1 meter away from the starting point, is there. 2 meters, 3 meters, 4 meters, 5, 6, 7, 8. So 8 meters away and hasn't moved yet at the same time. So this is not something that's possible. Vertical line is not possible. You cannot be in infinite positions at the same moment of time. Well, that's all we have for you tonight. So hopefully this was helpful, and we'll catch you next time when we talk about how to calculate acceleration and how to graph acceleration. See ya!